Welcome to this video tutorial on N-channel MOSFETs, commonly referred to as n-MOSFETs. Let's start by understanding the basic structure of an n-MOSFET. An n-MOSFET has four main terminals: the drain, the source, the gate, and the body. 1. Drain, this is where the current flows out. 2. Source, this is where the current flows in. 3. Gate, this terminal controls the flow of current between the drain and the source. 4. Body, this is the substrate of the MOSFET, often connected to the source in n-MOSFETs to simplify the circuit. Now, let's focus on the circuit shown in the diagram. We have a power supply providing 5 volts. This is connected to the drain of our n-MOSFET. The source is connected to ground, and the gate is receiving a voltage of 3.4 volts. The current flow in this circuit is 34.2 milliamps, as indicated. To understand how this current flows, we need to delve into the operation of the n-MOSFET. The key to this operation is the voltage applied to the gate terminal. Let's talk about the gate source voltage, abbreviated as V_GS. The voltage between the gate and the source is known as V_GS. In our circuit, V_GS is 3.4 volts. What is the threshold voltage, abbreviated as V_TH? The threshold voltage is the minimum gate-to-source voltage required to create a conductive path between the drain and the source. For an n-MOSFET, this is typically around 2 to 4 volts. In our case, since V_GS is 3.4 volts, it is above the threshold voltage, which means our n-MOSFET is turned on. What happens when the n-MOSFET is in on state? When V_GS is greater than V_TH, a conductive channel forms between the drain and the source, allowing current to flow. This is exactly what's happening in our circuit. The amount of current that flows depends on the gate voltage and the resistance of the channel. In our case, the current flow is 34.2 milliamps. Now, let's discuss the drain source voltage, abbreviated as V_DS. The voltage between the drain and the source, V_DS, determines the region of operation of the MOSFET. In our circuit, the source is connected to ground, and the drain is at 5 volts, so V_DS is approximately 5 volts. Regions of operation. The MOSFET can operate in different regions based on V_DS. 1. Linear region. When V_DS is low, the MOSFET acts like a variable resistor. 2. Saturation region. When V_DS is high, the MOSFET allows a constant current to flow, controlled by V_GS. Visualizing the circuit. In the diagram, you can see the gate voltage set at 3.4 volts, which turns on the n-MOSFET, allowing current to flow from the drain to the source. The ammeter in the circuit shows that the current flowing is 34.2 milliamps. On the right, there is a graph showing the behavior of the MOSFET. The yellow line represents the voltage across the MOSFET, V_DS, while the green line shows the current flowing through the MOSFET. Practical application. This simple circuit illustrates how an n-MOSFET can be used as a switch or an amplifier. By varying the gate voltage, you can control the current flow through the MOSFET, making it a versatile component in both digital and analog electronics. Conclusion. To summarize, an n-MOSFET operates based on the voltage applied to the gate terminal. When this voltage exceeds the threshold voltage, a conductive channel forms, allowing current to flow from the drain to the source. Understanding this basic principle is fundamental in electronics, and it can be applied in various practical circuits. Thank you for watching this tutorial on n-MOSFETs. We hope you now have a clear understanding of how they work and how they can be used in electronic circuits.